Okay, let's get started here. Good evening and welcome to the North Jersey Astronomical Group. This is our June meeting, and tonight we have a nice presentation set up for you, and so we're going to get started with that. Members, please stick around. Afterwards, we're going to have a short business meeting. Got a few things to discuss before summer starts, and so let's get started. Mary Lou, do you want to introduce our speaker tonight?
Sure. So I'd like to introduce Ron Wilcox, who's a ham radio operator, lives in Utah now, grew up in California, and eventually got his way to Utah, where he says it's lovely and it's wonderful, and the wildfires are not as bad as they are in California. So it's a good thing to know out there. So he and I are both ham radio operators. That's how I met him. And we're very interested in the upper layer of the atmosphere, the ionosphere, and the Earth is like many planets having an ionosphere, and we're going to hear about what it is and how it gets affected by the sun and solar flares and whatnot. So I'd like to introduce Ron now. Go for it.
All right, well, greetings everybody. Let's get this. See if we can get this on, and then I'll do a little bit of an intro here. And we'll try this. Hopefully everybody can see this. So, as Mary said, my name's Ron. I've got a medical background. I'm a nurse case manager, but I've been in ham radio off and on since 1984, thoroughly enjoyed it. Loved science in high school, so I've always enjoyed any form of science my whole life. About 4 or 5 years ago, I had some of my friends that went to a presentation on propagation and radio propagation, and they came out and they said, just had no clue, and they wished that somebody had a more basic introduction to it. And that's where this presentation has come from. Most of my presentations have been to ham radio operators, so you'll probably see that kind of a bend in the presentation. And I've done presentations pretty much different places in the nation. People have seen it and asked me to. And the last one I did was for the QSO Today convention, which was a little larger than I was used to. I think they told me I had 3,220 people watching it. A lot of questions afterwards. I will throw out a quick disclaimer. I am not an astronomer, and I'm not a physicist. I just have a passion and super enjoy this whole topic. And again, this was made for some basic. So I'm hoping there's something for everybody here, whether it's a lot or a little, that you didn't know before, but if not, just bear with me and enjoy the pictures as we go through this. It generally runs me about 30 to 40 minutes to do it from beginning to end. And then if we've got questions, we can go from there. Or if somebody sees some questions in the chat, let me know and I'll be glad to stop. Please be aware, I may say I don't know, or I may say, you know, that's really kind of past the scope of what I'm trying to accomplish with this here. So with that, good evening, everybody. It's just really nice to be with your group. And so I thought it was pretty cool that your organization has been promoting astronomy since 1981. As I went into your Facebook page and into your website and did some reading about your group and looked at a bunch of your pictures and things. So greetings from Utah. So I've titled this From the Sun to the Ionosphere, as we're going to cover some of those basics for that area. Let's talk a little bit about the sun. The sun is 93 million miles from the Earth. If you were to see how many Earths you could put inside of the sun, it would be approximately 1,300,000 Earths. The sun makes up right around 99.86% of the solar system, of the mass, the planets, the asteroids, etc. inside of the sun, we have the core. And in the core is where we have hydrogen fusing into helium. This creates a tremendous amount of heat and energy. It's parts of it is a plasma, and let's define that. A plasma is a gas. It's another state of matter. It's where we have ionized or charged particles. So this heat, this energy, that's coming up from the core of the sun can take up to 100,000 years before it comes to the surface of the sun as it migrates and makes its journey. The temperatures, the core temperature in the sun is 29 million degrees. The maximum surface temperature is a mere 18,000 degrees. And then as you go above the surface of the sun, the temperature rises again, goes to 2 million degrees. And then recently they have found out that there was theories about it, but they have found out now that is due to the magnetic waves that let's talk a little bit about the solar wind. The solar wind is a continuous flow of atomic particles, and it comes outward from the sun and it goes in all directions, not just towards the earth. And it's never ending, it's always coming out. And it comes from the coronal plasma. And you have two kinds of solar wind. You have a slow solar wind that takes about 4 days to get to Earth. And then you have a faster one that makes it in about 2 days. The slow one tends to come from the middle latitudes of the sun, and it goes at a paltry 200 miles per second. The fast solar wind is usually associated with coronal holes, and it is found more at the poles of the sun and the higher latitudes of the sun. And this is what a coronal hole looks like. And this is an artist's conception of that solar wind coming and pushing against the Earth and the magnetosphere of the Earth. And another artist's conception of it. Let's talk a little bit about sunspots. For a ham radio operator, sunspots, this is a huge deal because when we get sunspots, we have increased propagation. Some of the early theories that other scientists and people and the press thought, there was one newspaper that swore that it was that they had dirty telescopes, and if the astronomers would just clean their telescopes, that they would get rid of these spots that were being seen on the sun. Another very prominent theory was that these were huge mountains on the sun, and that at the top of the mountains it was colder than on the sun, and that's what caused that dark sunspot color. There was another very prominent theory in that the sun was surrounded or completely covered in clouds, and that every once in a while there would be a break in the clouds, and that's how you would see a sunspot. Now, sunspots are in cycles, and the cycles are approximately 11 years with a maximum and a minimum. One complete solar cycle is right around 22 years. The most intense solar cycle that we've ever had was in 1954 when it started, and that was cycle 19. And we've never had anything like cycle 19 before or since. The smallest cycle on record was the one that we just got done with, and that was cycle 24. And the solar cycle right now is 25. And there is a lot of interesting work being done and a lot of predictions and theories. There is a small group that feels that it could be a huge solar cycle this time, but the majority of the scientists are saying it's going to be maybe slightly larger than, a little bit larger than 24, but nothing stupendous. Now here are some sunspot observations. I really liked this graph. If you notice there in the red, there's something called the Maunder minimum. And this was a period of time when there was literally for, I think it was something like 80 years, there was almost no sunspots ever seen. Something very, very interesting with this was that in Europe and parts of Asia, they had some of the coldest winters on record since early BC times. They don't really think or know how there could be a relationship on that, but it's just an interesting statistic. There was another minimum called the Dalton minimum. It started around the 1800s, and it was not near as low as the Maunder. Then if you look the modern maximum, you see around 1950, that cycle 19 that was so high. And information on sunspots, it really, we have a lot of information. The Chinese actually kept records of sunspots, but that's a whole nother presentation on the history of sunspots and how we record them and different changes to that. So where are sunspots located? At a solar minimum, sunspots will start towards the middle latitudes of the sun. As the cycle will progress towards a maximum, these sunspots will tend to migrate towards the equator, and you'll tend to see them there. And they move east to west, and they're usually visible for about 13 days. Now in this picture, you've got cycle 24, which is the new cycle coming in, and you've got cycle 23. And so the cycle 23 is the older one, and the sunspots have migrated towards the equator, whereas the 24 in this picture is the new one, and it's up in the middle and higher latitudes. The sun rotates with an unequal distribution. So if you see there, you've got in the middle, in the equator, generally it's about 25 days, but up towards the poles, it's closer to 35 days. And this is very important as to understanding how we get sunspots. And I'm having to go a little slow because I can't get my space bar or my enter key to work. So I'm using the wheel on my mouse and trying to make sure I don't go through 10 slides really quick. So what'll happen is underneath the surface of the sun, close to the surface, you have magnetic fields. It looks kind of like a slinky underneath the surface. And these magnetic fields, they are longitudinal. In other words, the magnetic fields run north to south or south to north, but they run longitudinal. But as I mentioned earlier, the rotation speeds between the equator and the poles are very different. And this slowly will cause a bending and a distortion of these magnetic fields until pretty soon they are almost east and west. This distortion brings a tremendous amount of energy, and eventually these magnetic fields will break through the surface of the sun. And when this happens, there will be huge magnetic loops with cooling, and we now have a sunspot. And here's a more visual representation of that. In the first one, we've got the magnetic lines going north-south longitudinal. And then as the sun spins, it starts to distort and bend these lines until pretty soon these magnetic fields are running east to west with all that distortion and all that energy. And then you'll see that sunspot will all of a sudden break through, and you'll have a magnetic field, and it will trap a lot of energy in it. And again, it kind of looks like a slinky as these fields go around. You will sometimes have these magnetic fields that they will pinch off and break off, and then we have a solar flare being released, and the magnetic field will reform. And that's a whole nother presentation just on that. How long and how big? So a sunspot can range in size from a really small one that's a few hundred miles across to a large one that can be 250,000 miles in size. And the lifetime of a sunspot, a few days to sometimes they will even last several months, and you'll keep seeing them as they rotate into sight, or as the stereo satellites will see them. Why are they dark? Well, a sunspot, the actual area where the magnetic field has broken through, is 30% cooler than their surroundings around them, and that's why they're darker. We have something called a smooth sunspot number. If you were to graph and look at the daily numbers and the monthly numbers, they're very spiky. They're very difficult to do anything where you want to quantify. The fluctuations are all over the place. So what they finally decided is that they would take a date and they would use the data from 6 months behind and 6 months after, and that gives you a smooth sunspot number. And these numbers are somewhat subjective. Their increase in numbers is associated with an increased ultraviolet radiation being sent out from the sun. And when we talk about the ionosphere, we will see that this leads to improved radio propagation and higher bands, which means bands that are a higher frequency and a shorter wavelength will open up as you have that extreme ultraviolet coming into the ionosphere. The area around the sunspot is where we actually get this ultraviolet radiation. So it doesn't really come from the sunspot itself, but it comes from the area around. Let's talk about the next thing. After World War II, shortly after, I think it was like just a year or two after, it was discovered that there was a radio energy in the microwave range. It was 10.7 centimeters, this radio energy. They called it the solar flux. Then they discovered that the number of the solar flux was very closely correlated to the number of sunspots present. So if the solar flux went up, it was an indicator sunspots were going up. And it would give you, the solar flux would give you a very good indicator if on the radio that you'd be able to communicate at a greater distance. It's important to realize the solar flux does not cause any ionization. It's just that it's another radio energy from the sun, but that it correlates very closely to sunspots. Oh, and you'll also sometimes see it called the 10.7 centimeter flux index, as well as the solar flux or the solar flux index. It's reported daily. If you're in ham radio and you're doing any DXing, and DXing is a term that we use for wanting to work entities and countries and to get as many as you can, is something that I really enjoy. So the solar flux is watched pretty closely, and there's a report that comes out with it. Its values can go from a low of 60 up to as high as 300. We actually were down in the 60s at the end of this last solar cycle. And with low values, conditions not very good usually. At the peak of an average sunspot cycle, your solar flux will usually be above 200, a little bit above 200 most days. If you've had the solar flux drop, it will take a few days of higher values for conditions to improve. So while there's a correlation, the solar flux goes up, you're not going to immediately see that the sunspots go up. Now let's talk about a solar flare. I very commonly will hear people talk about solar flares and CMEs, or coronal mass ejections, as if they're the same thing. So a solar flare is a very brief, intense, very high energy eruption from the sun, and is caused by tangling, crossing or reorganizing of the magnetic field lines near the sunspots. So that picture I showed you earlier and those magnetic fields, they will sometimes pinch off. And when they do, the eruption is very intense. Solar flares are fast. They will go at least half the speed of light, which means they are 8 to 10 minutes to Earth or a little bit more. Solar flares can affect power grids, radio communication, satellites, and they're often associated with CMEs. And this is a coronal mass ejection. They have different classifications. The one that you'll see the most is that there's a C, which is a small flare, will have minimal impact to propagation. There's an M. We just had a flare released, I think it was on Monday. Today we had a CME, but it was an M class. And that's, an M will start affecting propagation. X definitely will affect radio propagation. And like the Richter scale for earthquakes, each letter, CMX, represents a 10-fold increase in the energy output for a solar flare. Now let's talk about the big boys here, the coronal mass ejections. These are large expulsions of plasma and magnetic fields. They can literally eject billions of tons in one mass ejection of all this coronal material. They average 2 to 3 days to reach Earth. Some are slower, some are faster. The CME heading this way right now. There's one group that thinks it'll be here. I think it's NASA thinks it's going to be here tomorrow morning. And I believe NOAA is saying tomorrow afternoon. There's a coronal mass ejection, massive amount of material being sent out. And you can kind of see that round magnetic field. So let's talk about some of these CMEs, these huge, great geomagnetic storms that have hit the Earth. May 1921, from May 13th to May 15th, this was part of solar cycle 15. It sparked a number of fires worldwide. There was one in New York at the Grand Central Terminal, and it came to be called the New York Railroad Storm in the press. This sunspot was estimated to be 94,000 by 21,000 miles. Another fire broke out in the Central New England Railroad Station, and it completely burned it. In Sweden, there was a big telephone station that was burned up. And in the press, they first started saying it was a comet. And then the press said, no, it was the Aurora Borealis. And then the scientists said they weren't really too sure what it was, but it was neither one of those. The impacts from this storm were global. There was reports of disruption from Australia, Brazil, Denmark, Japan, New Zealand, United States, all over the place. 1921. Here's one in 1972. Back when I was getting ready to, after I'd graduated from high school and everything. So it was an X class. It had white light, which is unusual and shows intense energy. It was an X plus a 20, and it had a lot of gamma rays, which is only in your very, very high energy CMEs. It destabilized portions of the North American power grid. And on August 4th, we still had Vietnam going on. The storm caused the accidental detonation of numerous US naval mines because they would be magnetic, pick up the metal from the ships, and near Haiphong in North Vietnam. In fact, in some new information that was released, I don't know, I think it was like 5 years ago from the Pentagon, there was actually communication going on because the ships in the area thought that we were being attacked and that our mines were being sent off, and they didn't know how it was happening. This particular CME, its transit time was 14.6 hours is what they figure. This is the fastest ever recorded for a CME. Now remember, this is before we really knew what CMEs were. Scientists have gone back and used the data to find all this out. Storming continued for a couple of days, and they even had bright red, which is quite a rare color to have with a CME. 1989, this was called the year of the turbulent sun, and this is the peak of cycle 22. In Quebec, there was a major power failure, and also in parts of northeastern US. Probably you folks in New Jersey might have been involved in that. The electrical supply, the grid went off, and 6 million people were out of electricity for 9 hours. Auroras were seen all the way down to Texas. And HF, which is high frequency, and this is generally considered to be in your around 80 meters or 3.5 megahertz up to about 30 megahertz or 10 meters long as an HF. There was extended blackouts where nobody could hear anything on the radios. A lot of satellites, we had just started to put satellites up. Many of them were damaged, and many satellites had to be reset. March 6th to March 19th, this is incredible. 48 M-class and 11 X-class flares were launched towards the Earth. Now, one of the largest events we know of it has been called the Carrington event. This occurred in 1869. It reached Earth in 17 hours. Sparks would shower from telegraph machines, shocking the operators. There was many, many stories of operators being at the table, and all of a sudden the papers on the table catching on fire, and they were able to operate their telegraph keys with no battery, no power. Many of them got shocks, got their hands burned when they tried to touch them. And all over the planet Earth that was facing the sun, there were colorful auroras covering the Earth. In fact, it glowed so brightly that we have many reports that birds began to chirp, and people got up and got dressed, did their chores, getting ready to go to work, thinking the sun was rising. There were people that began to head to their church, thinking the end of the world was at hand. I believe this is supposed to be somewhere in Colorado. Sorry, I forget which one it is. Now there's a new one I was just reading about, Scientific American. I think I have the source in my references at the end, and I'm going to mispronounce this. I apologize now. I didn't look it up, but it's called a Miyake event after a scientist by the name of Fusa Miyake at Nagoya University. I do not speak Japanese. I completely apologize if I just butchered that. Anyway, they've been doing research, and he's leading this group, and they are finding events back in the history of the Earth that go 10 to 100 times stronger than the Carrington event. And they think they found 3 for sure: 71, 76 BC, 52, 59 BC, and AD 775. And I think in the article, there's like 6 others that they're just not sure on, that they're still checking. Kind of an interesting new thing. Earth's magnetic field. This is also the geomagnetic field. High energy particles from the sun can disrupt the Earth's magnetic field. This will cause a tail on the backside of the Earth and the backside of this magnetic field, and is called the magnetotail. Think of a rock in a stream. A magnetometer is a device that measures magnetism, the direction, the strength, or the relative change of a magnetic field at a particular location where that magnetometer is placed. Now, the reason I bring up magnetometers in the geomagnetic field is that, at least in ham radio, we use 2 indices. We have one called the A index and one called the K index. And there are reports all the time. They are put out by NOAA, and there's I believe it's Belgium, and Germany, and they have these reports that come out. It gives us an idea of the severity of magnetic fluctuations in the Earth's magnetic fields. This is extremely simplistic, and it uses 13 magnetometer sites. There's many others, but for the A and K index, that's what we're using. The K index is measured every 3 hours. If we take all 13 sites on the globe, we now call it a KP index or a K planetary index. It goes from 0 to 9. 0 is quiet, 9 is severe, and then 3 or below, you can have it may indicate good propagation. This is not an absolute, but it's another tool that we use for propagation. And the lower the number, the better the odds that we'll have good propagation. Now we have the A index. The K index, remember, is every 3 hours. The A index is every 24 hours. So we take 8 K readings every 3 hours, 8 times. This gives us a daily average, and it goes from 0 to 400. 15 or below, good propagation. Now, if we take the A index and we take all of the 13 readings, the 13 K readings, we call it the AP or the A planetary index. Let me make sure I didn't skip one there. Now let's talk a little bit about the ionosphere. The ionosphere is regions surrounding the Earth. We used to call them layers, and I still say layers. I try not to, but they're actually regions. In their center is where they're the most dense in terms of ions, electrons, and they have the lowest density at their edges. All of the regions in the ionosphere have ionization, but each region has a specific characteristic. This area is plasma. And what we're doing is we're talking about refraction or bending. The electron density, how many electrons we have, is the controlling factor. Neutral atoms, which is mainly oxygen and nitrogen, small amounts of helium, argon, hydrogen in the lower levels of the ionosphere, but mainly oxygen and nitrogen. And as you go out from the Earth in the ionosphere, more and more of it is oxygen. Because these ions are neutral, there is no charge for a radio wave to interact with. But when ultraviolet rays from the sun enter the ionosphere and strike these ions, they have enough energy that they will separate the electron. And then this will give us our positive ion and the negatively charged electron. And as I mentioned a minute ago, the electron density is the key factor when we're talking about the propagation and the refraction of radio waves. From the Earth extending up, the density of neutral atoms is reduced. We have less and less of these ions. The less density that we have, the longer it takes an electron to find another nucleus and recombine. So we have more electrons and they tend to stay in their negative state longer. One important thing to remember, and again, this is geared towards ham radio, so I'm not too sure how to change it around, but our radio waves, as they leave the Earth, the amount of loss to those radio waves increases as the frequency of the radio wave decreases. So the higher the frequency, the less loss. The lower the frequency, the greater loss. So let's talk about the different regions in the ionosphere. The lowest one is 40 to 60 miles above the Earth. It's considered to be a daytime region. Generally, about 30 minutes after sundown, it is gone. This one is the closest to the Earth's surface. It has the greatest density of atoms, causing the ions to rapidly recombine back into a neutral ion, a neutral particle. So it's horrible for any kind of propagation. Now, remember what I said earlier is that the higher the frequency, the less absorbed. So lower frequencies, such as 160 meters, 80 meters, 40 meters, are drastically affected. And they lose their energy, and there's just no propagation during the day with those frequencies. Radio waves going through here in these lower frequencies are absorbed rather than being refracted. In fact, one of our experts in the field, Carl, K9LA, quote, called it a giant attenuator or an RF sponge. The other interesting thing about the D region is it is the least understood of all the regions, and is the chemistry is the least understood. The nature of the D region is the least understood, and it's supposed to be the most complex, according to Dr. Scove. Next, we have the E region. This is a pretty thin region. It's only about 6 miles thick. It's about 60 to 70 miles up. We get some propagation here. The electrons and positive ions combine fairly quickly, but nothing like the D region. This is the lowest region that begins to refract radio signals and support propagation. And it also is mainly a daytime region. Now we have something called sporadic E. This usually is about 65 miles up, about the same height as the E layer, hence the name sporadic E. It comes and goes irregularly. I have heard other people call them regions, patches, clouds. They have a very defined geographical characteristic. They're fairly thin, and they're about 50 to 100 miles wide. We think that they can move up to a maximum of a few hundred miles per hour. Some of the current ideas is a plasma instability, plasma bubble, or disturbed magnetic activity, or one that I'm seeing more and more of is that it's metallic ions from meteors that are captured there. The F region, as we start to wrap this up. You have an F1 and an F2. The F region becomes smaller from the bottom up at about 700 meters every second right after sundown. So as soon as the sun goes down, starts to go down, you'll see the F region become much smaller. It rises and falls with the rise. This is F1, I'm sorry. F1 layer, part of the F layer. You have F1 and F2. F1 is definitely rises and falls with the rise and setting of the sun. It will disappear at night. It's similar to the E layer, except it has much better propagation. The maximum ionization for F1 is right around noon. F2, this is the one that ham radio operators absolutely love. It exists during the day and the night. This is the most ionized layer. And if you're a ham radio operator doing DX, this is the one that's the most important. F2 is in a constant state of motion. It's way beyond the level of what I want to do with this, but there are so many different things about the ionosphere that affect it. All kinds of different currents. And there's things that are called L layers of the magnetic field that can affect the ionosphere. And there's different, they call them scintillations. And I mean, it's fascinating. And I absolutely am not an expert, just somebody that loves to study this. The ionization increases sharply just before sunrise, and its densest electron numbers are found on winter days. So that's my presentation. Some great resources from a ham radio perspective. is K9LA, his website, some incredible things. Don at W3LPL, there's a Contest University, and Dr. Tamantha Scove on her website has what she calls her mini courses. They're about 2 hours each, and she starts at the sun, works her way to the earth, and then down to the surface of the earth, everything from gravity waves and how the volcanoes affect the planet. And then of course, there's the ham sci, and the things I'm just starting to learn about with TIDs, traveling ionospheric disturbances, just a wealth of really fascinating information out there. Here are some of my references that I've used for this presentation. And that's all I've got. Now, I really, really hope that this was not way below everybody's level. I'm honest, I'll be honest with you, I was a little hesitant about doing this presentation when I heard it was an astronomy group, and I pictured all these people that would be going, ho hum, learned this 40 years ago. But hopefully at least it might have been a review or something of interest to your group. And now I'll entertain questions. With that caveat, I may say, I don't know, or I don't want to get quite that deep. So I'll turn it over to if anybody has a question.
Sure. Cliff has his hand up. Cliff, go ahead.
Howdy, Rod. I was surprised and dismayed to learn that there may have been events that made the Carrington event look like a spark in the dark. But just thinking about the Carrington event itself, back when it happened, the only real electrical infrastructure we had was the telegraph system, and it caused enough damage there. I had read somewhere that if we had something like the Carrington event happen today, it would essentially burn out all the high voltage transformers of the power grid. And there aren't spares. They have to be ordered one at a time. They have to be made at a factory that needs electrical power to operate. Is that a true statement? Would they really burn out all the high voltage transformers of the power grid?
Yes and no. How's that for, realize I'm a medical person, okay? Yes and no. Yes, your test results are not good, but yes, we're going to do more labs and draw more blood. So yes and no for this reason. Starting with 1989, with that large one that happened, there was a huge study and start from the electric companies in Canada, the United States, and in Europe somewhat, but really in Canada, the United States, as to what do we do if this comes again? They didn't really understand everything of what it was, but they did know it came from the sun and that it was a high energy. And then also there was another one that we had, and I didn't want to put them all in. I just tried to put a few that were scattered. I mean, if I was to put all of them in, it would have taken the whole lecture. But there was another one in the early 2000s. And from this, the electrical industry learned a whole bunch about how to put in some safeguards and things that they can do. So they have done a lot of work quietly to stabilize the electric grid across the two nations, but they are not even nearly complete in this. And if we did have something like this, we could have some very, very significant failures that could happen. So that's why I said yes and no, that there's been a lot of progress made, but that there still is a lot to do. And I know that even when we have a small flare or CME, maybe you already knew this, but in the International Space Station, the ISS, they actually have a safe room, and they'll have the astronauts crawl into that to be safe when these radiation storms go through. But it's probably not a very good answer to your question there, Cliff, but that's, to my knowledge, that's the best answer I can give you, is progress, but a ways to go. And yeah, they'll short circuit. That's what happened in 1989, is they actually short circuited some of the transformers and substations and all that kind of stuff. And it took a while to be able to replace them and get things back up again.
I have a question.
Yeah.
What do they actually do to safeguard against the short circuiting of the transformers, I assume? Do they just clamp it down, and when it detects a sharp rise in the current?
So here's my honest answer. I read an article, I think it was in Scientific American, about this, thought it was fascinating, and can only remember about 10% of it today. But what I remember is it had something to do, it wasn't just like grounding it so that things would go to ground, because with the magnetic fields coming in and that magnetic field creating inductance and creating an electrical current, it wasn't enough to just do a better ground. But they have designed transformers and designed the grid so that it can handle the inductance. And anything past that, you have my apology, because that's the biggest thing I remember. But it was a very interesting article showing how they had set it up so that it could handle a much higher inductance without burning up, which a lot of them did. They didn't explode, but they did catch on fire. So not a very good answer, but the best one I can give you at this time.
Yeah. Thank you.
Yeah, this is Anant. I have a quick
Yeah, go
question.
ahead.
Yeah, thanks, Kevin. So Ron, great presentation. Thank you for that. It was very informative. Now, I just want to get your take on what is the effect of increased CO2 concentration on the ionosphere?
The CO2 concentration, as I understand it, is not a huge player with the ionosphere, but it would be a much greater player with the, and they use two terms, the mesosphere is kind of where we start to also get the ionosphere, which can be confusing. And at one point I showed some stuff about it, and people gave me feedback and said, you lost me. So I just showed the ionosphere now, but you've got the troposphere, you've got the lower layers, and that's where the CO2, acid rain, and other things, and it has a much greater impact there. With the ionosphere, what you're looking at is, like, for example, the aurora borealis. You're seeing the Earth's geomagnetic field is a dipole magnet. And the magnetic fields come up out of the poles, back around and into the poles. And then some of them come at lower latitudes and lower latitudes. And with that energy at the poles, you have that the electrons start to separate. So you get your colors. Oxygen is the primary one, sometimes hydrogen. And so those are affected in their ionic state, but the CO2, I have not read anything except that it says that their main impact is much lower down in the atmosphere.
Thank you, Ron.
You bet.
So so that was my question. I was going to ask about the connection with the auroras, but I think, Ron, you just answered it when you talked about the magnetic poles. So when there's a sun flare up, we're more likely to be able to see the color, the aurora in the sky, because of how it impacts the magnetic field at the poles of the Earth. Is that what you're saying?
Exactly. Again, I don't usually include this because feedback is that it gets confusing for people. So let me go back to it's a dipole magnet. So you're going to have a north pole and a south pole, and the Earth's geomagnetic field is a dipole magnet. But you have layers of magnetic fields, and where they enter the Earth, those entrance points, depending upon the energy level, it's called an L level, but at those entrance points, they will move down in latitude on the Earth. And so if you're affecting, just to give it a name, let's use L5, L4, and L3. I'm hoping that's the least confusing way to do it. L5 is the farthest from the Earth, and it actually is almost right at the North and South Pole. L4 is going to be a little bit farther down where it enters and exits, and L3 a little bit farther. If you excite the L5 level, your auroras are mainly going to be up at the poles where these magnetic fields enter. If you excite the L5 and the L4, then you'll have auroras lower latitudes where the L4 also enters the Earth. If you had the L3, you're even going to have it farther down. And so as you excite these levels, these magnetic fields where they enter, the auroras will go farther and be seen farther and farther down, because the aurora is the geomagnetic field, and it is showing oxygen, sometimes nitrogen, others rarely. It is showing those ions and electrons and that energy, and you're seeing the color of that energy. And I'm trying to be careful, but again, please realize I'm normally talking to ham radio operators, and so I have to be pretty careful because a lot of them don't have a background and I can lose them pretty easy. So I don't really have good pictures that would illustrate this, but I'm trying to help you to picture in your mind. So Linda, I hope that was a little better. And
Yes, I so appreciate your pitch too. I'm a social worker. So, so the slinky image, you know, how you describe it is very, very helpful to me. I'm a beginner.
Yeah, and I'm a nurse, so, but I just love this stuff. I just started in with the ham side group, and this rookie, I'll tell you what, the people in that group have been so gracious to me. I'm sure they're thinking on the side, is there a reason we have an RN sitting in here listening to this stuff? But I really enjoy their meetings. So, but yeah, that Linda, that, and again, that's still a fairly simplistic, but that's how I like to describe the auroras and how they work. To me, that's how I picture it. So hopefully that, any other questions? All right.
So I have a comment about the aurora. In one of the really big events, I don't know which one it was, perhaps the one in 1989, I don't know. I thought it was very funny that the auroras were really, really active because there was so much plasma coming from the sun that it impinged on the Earth, both at the poles and then at the L4 and L3 layers down closer and closer toward the equator. And in Texas, they had people seeing auroras that had never seen them before. So mostly you get a red glow in the sky, in the northern part of the sky. And so a group of people in Texas looked to the north and saw all this red glow and thought that the town north of them was on fire. So they sent their fire engines north on the road to get to this town and help put out the fire. But then the town south of them saw the glow as well, and they sent fire engines north on the highway. And eventually they had 4 or 5 towns worth of fire engines going north, trying to find where the fire was to put it out. And it was just in the sky and not in the towns at all. And it was very funny to hear about that.
Oh yeah, there are, and I didn't have time, but there are some very, from funny to interesting stories. Like the Carrington event, there's this one telegraph operator, and he talks about hearing a noise and going out of his little shack, his little building, and he saw these big balls of fire going up and down the telegraph lines, and it just absolutely terrified him. And he was sure that it was the last days and that the forces of evil were coming, and he was done with the whole thing. And another guy said, I had an important message to send, but every time I touched the telegraph key, I got burnt. But he said, I thought it was something with the equipment. So I just kept trying to reach it to send my important message, and I just kept getting burnt and burnt. and he didn't realize it was going to be there for hours. Yeah, there's just all kinds of interesting things that associated with that. And those auroras, for people that haven't seen them, yeah, they're a lot of interesting stories with that.
So have you ever seen an aurora, Ron?
Yes.
Tell us about it. Where were you?
I've seen them when I lived up in Seattle. I've seen them when I was up in Idaho. I was in Idaho. I was a scout leader long time ago, back when backpacking was easy to do. I'm too old for that now, but and I can remember sometimes when we'd get up in the mountains in central and northern Idaho and go backpacking, that we would sometimes see some auroras associated with that. I haven't really seen any down here in Utah or California, but in Washington and Idaho. And the ones that I saw, they were just all green. There was no other colors associated. And it was what we call the sheet aurora.
Yes.
So
I think we need a road trip, folks.
We got one in July.
Dr. Scove, in her weekly broadcast that she does, she will have pictures sent to her by aurora photographers. Sometimes they're average, but boy, sometimes she has the most incredible photographs every week of auroras that are going on, and people that travel to take pictures and send them to her. So any other questions? All right, folks. Well, again, I'm just an amateur. I'm not a scientist. I just have something I
have one
love,
more question.
something I love to study. Oh, another question? Go for it.
Just a comment. In 1965 at Stellafane, I saw a beautiful auroral display and even had some what looked like phaser banks shooting from the Enterprise on it, but it was green in color, and it was clearly green to my naked eye. It was not a photograph, and I was very surprised. A couple years ago, a couple of our members, AAI, attended a tour of northern Norway to see an aurora, and the person leading the tour told them that, oh, you can't see color in auroras with the naked eye, you can only photograph it. And I know darn well I've seen green, so.
Oh, yeah.
And I've seen red as well.
Yeah, I've seen red as well, too. Yeah.
Yeah. Well, I've only seen the green. I've seen the red in pictures. Personally, I've only seen the green, so.
I've seen both too. I think it was somewhere in the early 2000s. I was up in Ithaca, and it was definitely a green.
Yeah.
Or at that time, during that last maximum.
Okay, well, great presentation. Thank you very much, Ron, for being with us tonight. And so that's great.
My pleasure. It's time for dinner out here. I've got dinner waiting, so I'm going to go grab a bite to eat, and I will see all of you folks later.
Thank you very much.
Thank you.
Best of luck with your association, and hope you have great things in the future, and thank you for your courtesy.
Okay.
Thanks, Ron.